Okay, so today the reading assignment was kind of shorter in terms of starting with alkanes. Monday we'll get into the start of naming, and I fully expect on Monday you may have a lot of questions because naming is going to involve a lot of rules that you've never probably seen those kinds of problems before. So we're going to work through naming next week. All right. So what kinds of questions did you have about? Today's stuff, orbitals, resonance structures.
I just had like kind of a general question. So there was questions 1, 2, 3, and 5 for the hydrocarbon section, but I didn't see them in the reading. Were they like in the other folder, like the hydrocarbon folder that we had?
I thought they were. They might. Are they past section 2.2?
Yeah.
Okay. Then I guess you won't be doing those, or didn't do those. So they're. I thought I looked and I thought they were in the first reading, but maybe not. So they'll go into Mondays. Because those questions like what's a primary or secondary carbon, I thought that more fit into naming, but.
Just do like a practice orbital picture problem.
Sure, we can do that. What kind of molecule? You want some multiple bonds?
Yeah.
Double, triple?
Let's do
Triple bond. Okay. Something like that. Okay, so first step. First step I need to know is for all the non-hydrogen atoms, I need to know what the atom's hybridization is. Right, so I need to know what the hybridization is. So for this CH3, what would its hybridization be? I hear sp3. Agree? Sure is not necessarily agreeing. There's might be a little skepticism when we say sure. Skepticism on your part, like, okay. Does everybody know where the sp3 comes from? I don't. Somebody tell me. How do you get sp3? Okay, it's got 4 sigma bonds, no lone pairs. That means it's got 4 hybrid orbitals. How do we get 4 hybrid orbitals? sp3. Okay. What's the hybridization of this carbon? sp. And what's the hybridization of that carbon? sp as well. Okay, so that's the first step. We got to determine what the orbital or what the hybridizations are. Now we can go ahead and kind of sketch out the picture. What I should probably do here is write out the hydrogens on the CH3 group like this, so that we have a Lewis dot structure to kind of follow here. So we could start with the sp3 hybridized carbon. All sp3 hybridized atoms are going to look like this, except what I want to do is I want to point one of the orbitals horizontally because that's going to be this bond right here. It's going to be that. It's going to be this bond is going to go with that orbital.
So it's going to matter like the exact position you draw them in. You can't just know that there's like 4 clouds and draw them.
I mean, there can, but you're going to have to bond one of those 4 clouds with a C triple bond C. So if I'm going to draw it like I did up here, I want that orbital to be kind of horizontal. But if you want to make it down, you could do that as well. I'm just going to kind of mimic what's up here. By saying next, I've got 1, 2, 3 hydrogens, and so those are going to be the S. These are each sp3s sigma bonds to the hydrogen. Okay. Each of the carbons would have one unpaired electron in it, and then they pair it up with the hydrogens, one unpaired electron in the s orbital. So that takes care of the left-hand carbon. The middle carbon is sp hybridized. So what I would do is I would take my carbon, here's going to be hybrid orbital 1, here's going to be hybrid orbital 2. Each one of those has an unpaired electron, unhybridized p, and a second unhybridized p, each having one unpaired electron. So any element, the sp hybridized, is going to have the 2 lobes, the 2 hybridized lobes, and the 2 p orbitals. And in this case, since this is a carbon, each carbon's going to get one unpaired electron in each of the lobes. Okay. So then I would go ahead and form the sigma bond from those two to then match basically this sigma bond, the one that was bold. The last carbon on the right is going to be sp hybridized. So I'm going to have a carbon with, again, 2 hybrid orbitals and then 2 unhybridized orbitals. Each one of those orbitals gets an unpaired electron. On the end, there's my hydrogen carbon sigma bond. And then here's my sigma bond that holds the triple bond together. So remember, the sigma bonds can only come from the hybrid orbitals. You can't form sigma bonds from p orbitals, only hybrid ones. And s's, and 1s. Okay, so now we have that, so now we're going to form our pi bonds. So this structure right now would be the equivalent of this. It would be the equivalent of that Lewis dot structure. So now we would pair up the first pair of electrons to form the double bond. So you can choose your orbitals that you want, but I'm going to choose the orbitals that are up and down, and the other ones that are up and down. So those 2 lobes overlapping makes the first pi bond, which would be above and below the sigma bond. But they're in the plane of the screen. You can only overlap p orbitals if they are parallel to each other. So if you had like a py and a pz, you can't overlap them because they're not parallel. So that forms the first pi bond. Then these orbitals that I'm coloring here in red, those are the p orbitals that go in and out of the plane of the screen. So these ones are forward, these ones are backward, and so what I would then do is overlap those 2 orbitals to form the second pi bond. A pi bond is both lobes together, is a pi bond. So the one in front of the board and the one behind the board make up the one pi bond for that system. And so that would be the equivalent of doing that. And so that's what a triple bond would look like. You have 2 pi bonds, 1 sigma bond, and then in this case a sigma bond to the CH3, and a sigma bond to the CH of the triple bond. And so if you let the Lewis dot structure kind of guide you, like using this and then writing this structure, it can be a little bit easier to draw. Does that make sense?
I have a question about the like sp3 and then S sigma bond orbital. Would you have to like color in those bonds or shade in those bonds too because they're hybridized? Or
I mean, you could. The reason that I probably would have shaded them all in, I guess, here. I mean, I use the shading to tell the difference between a hybrid and a non-hybridized orbital. So I guess with an sp3, you could shade or not shade. And the shading or not shading is actually not what I'm going to grade. When you get this on an exam or a graded homework problem, when I take a look at this, I'm not necessarily going to be grading based on shading or not. I'm going to be grading based on how the orbital picture looks. So I know like if you had a C double bond O, people were kind of writing it like this. I know, I give them the same look. I'm like, what is that? I could see this, right? I could see, okay, this is the sigma bond, and then these two are the pi bonds. I could see that. But if you only have two lobes there, it's like you're missing something. Because the pi bond is the two p orbitals overlapping. So these are your pi bonds, and then in the middle is your sigma bond.
A triple bond, would it be like 5 lobes?
So if I was going to write my triple bond sort of like that, it would be like this. Here's my sigma bond, and then here's my first pi bond, and then here's my second pi bond. In and out of the plane. So it's basically, it's a hot dog in 2 buns. Right, if you took the 2 buns and you went like this, and then you put the other 2 buns like this, then the sigma bond would be in the center of it.
Can we go over one more time how you assign the electrons to each orbital?
So whenever I'm doing hybridization, I'm only hybridizing the orbitals. So let's do the C. Let's get out of that. Let's do a C double bond O like this. Okay. So let's say we wanted to sketch this. This is formaldehyde. So if I want to sketch this, same first step. What's the hybridization of the carbon? What's the hybridization of the oxygen? Oxygen's hybridization is sp2, and the carbon's hybridization is also sp2. Now, do they have to match up? No. They don't have to match up. That's why you got to determine each one individually. So what I would do now is let's sketch an sp2 hybridized carbon. So the carbon's going to have an sp2. So the way I'm going to draw this is kind of the way this picture is. So this is going to be these are my 3 hybrid orbitals. 2 form the sigma bonds with the hydrogen, and the top one is going to form the sigma bond to the oxygen, the way I've written it here, with the oxygen above the carbon. Now, in terms of putting electrons, well, let's see, I've got a p orbital, right? I've got an unhybridized p, which would probably go this way. So in this case, all 3 of the shaded orbitals are in the plane of the screen, and the p orbital is coming out and going back. Okay. So carbon, because remember the carbon has a 2s, 2p. In its excited state, it's got 1, 2, 3, 4 unpaired electrons. The Lewis dot structure for carbon is 4 unpaired electrons. that means into each one of these orbitals goes an unpaired electron. So one into p, both lobes, and one in each of the three sp3s, so sp2s. Okay. So we hybridize the orbitals, then we put the electrons into it. So the reason that carbon gets 4 is because in the excited state, carbon has 4 unpaired electrons. And you can also use the Lewis dot structure to tell you that it has 4. Now, what the hybridization for oxygen is also going to be sp2. So for the oxygen, I would say here's my one hybrid orbital, here's my second hybrid orbital, here's my third hybrid orbital. And then my unhybridized P is going to be parallel to the carbon, so it's going to be in and out of the plane of the board. Now, when placing the electrons into oxygen, I know that oxygen basically has a Lewis dot structure of 2 paired, 2 unpaired. Because for oxygen, it is a 2s2, 2p2, and then 2 extra p's, on 2 unpaired p's. And there's no d orbital to hybridize or to promote up into because there is no 2d orbital. So we're stuck. And so this gives that as my Lewis dot structure. So in the orbitals then I have to put 2 pair and 2 unpaired. Now the pairs can only go into hybrid orbitals. So the lone pairs have to go into the hybrid orbitals. The lone pairs cannot go into p orbitals. The only thing that can go into p orbitals is a single unpaired electron. So if I follow those rules then, and also I follow my Lewis dot structure, I'm going to have one unpaired electron here to pair up with the carbon, and then I'm going to have my other two lone pairs in the hybrid orbitals, and I can only put an unhybridized orbital into the p orbital. So the hybridization for oxygen and carbon look exactly the same. The orbitals look exactly the same. What's different is the number of electrons I'm putting in there, because oxygen gets 6 valence electrons and carbon only gets 4. Does that make sense?
How do you put the unhybridized p orbital with the oxygen?
Because whenever something is sp2 hybridized, that means it's 3 sp2 orbitals plus an unhybridized p. And so sp2 down here is going to have an unhybridized p. So if you think about all of these hybrids, how these hybrid orbitals, if you have an sp hybridized atom, you're going to have 2 sp hybridized orbitals, and then to get 4 orbitals, you need to have 2 unhybridized. So we're always going to have 4 orbitals. If you have sp2, you're going to have 3 sp2 hybridized orbitals, and what's the 4th orbital? The 4th orbital is the unhybridized p. And then if you have sp3, you're going to have 4 hybrid orbitals that are all sp3, and I've got 4 orbitals, so I don't need an unhybridized p. So it all went back to how we mixed the s's and the p's. So it has an unhybridized p. And then since the carbon has an unhybridized p, and since I know I have a pi bond here, I know I've got to have those 2 orbitals parallel to each other. And so by drawing them in this case parallel, they're now going to overlap to form the pi bond. The 2 sp2 hybrid orbitals are going to overlap to form the sigma bond. And then the s and the sp2 hybrid orbitals of the hydrogen-carbon bond are going to overlap to form 2 sigma bonds. Make sense? If it doesn't, you have to say something.
I got it when you did the first one, but when you did this one, I got it.
Which one? The whole problem?
The previous problem, that makes sense, but hybridizing this one, the second one didn't make sense.
The oxygen or the carbon? Both. Okay. I mean, the rule is you've got to find the hybridization of each atom first by looking at number of sigma bonds and the number of lone pairs. Once you find the hybridization, then you're just going to sketch out what that orbital looks like. So let's see. HCN. Or is it the double bond that's throwing you?
I don't think it's the double bond.
Okay. It's the process?
Yes.
Okay. Okay. So for this one, what's the hybridization of that C? SP. Because it's got 2 sigma bonds and lone pairs, so it's SP hybridized. How about the nitrogen? SP as well. Do they have to be do they have to match? No. Okay, so now let's sketch out an SP hybridized carbon. So the carbon that's SP hybridized is going to have 2 SP lobes. Vesper theory says they have to be 180 degrees away from each other. I now have 2 lobes. I need I have 2 orbitals here. I need a grand total of how many orbitals? 4. And so what's left over? If I've got sp2, I've got 2 sps plus 2 unhybridized p's. So now where are the unhybridized p's going to go? So now I've got a p orbital is both the top and the bottom lobe. Remember, they are clouds of electron density, so they're going to repel each other. So if you want, you could think of these as, this is one orbital but 2 lobes. So how many lobes do I have to fit into this carbon? I've got to fit a grand total of 4. 2 p orbitals but 4 lobes. So how am I going to fit in those 4 lobes? Well, I already have 2 lobes, so I could go back to Vesper theory and I could say, okay, I got 6 lobes. So what kind of geometry do I need to have? I got 6 clouds around the carbon. So it's going to have to be octahedral. Okay, it's going to have to be octahedral. So it's going to have to go like this. Sometimes I'll do this. X. X is any atom. There's an sp3 hybridized atom. All 4 lone pair, or all 4 hybrid orbitals. Geometry, tetrahedral. Okay, what's an sp2 look like? An sp2 is going to be, first of all, the 3 hybrid orbitals are going to be trigonal planar. And what's left over? Non-hybridized p. Now, that unhybridized p is 2 orbitals. I got 3. So that means I have to have a grand total of 5. 5 clouds, 5 balloons of electron density around the atom is going to be what geometry? Trigonal bipyramidal. So the p orbital has to go there. Okay. So that's the unhybridized p. Then if I have an sp, I'm going to have 2. I'm going to have 2 lobes of electron density. Vesper rules say they have to be 180 degrees away from each other. And now I have my other 2 p orbitals, each of which contains 2. So that means I have a grand total of 6 clouds of electron density around the atom. So it has to take on an octahedral geometry. So for carbon and oxygen and nitrogen, anything where we don't get into an expanded octet, these are the pictures that we would draw for that hybridized atom, with the shading being the hybrid orbitals and the not shading being the p orbitals. And so what we fit into this, just this generic structure, is the number of electrons, and that's going to vary whether it's carbon, nitrogen, or oxygen. So if I come to this sp hybridized carbon, it's going to look like that. If I look at the sp hybridized nitrogen, it's going to look like that. They're the same because they're sp2 hybridized. Sorry, sp hybridized. But now I need to place the electrons into the orbitals. Well, every hybrid orbital gets one unpaired electron. At least. So if I look at carbon, how many electrons do I have to place around it? 4. Why? Because carbon has 4 unpaired electrons. So that means 1, 2, 3, and 4. For nitrogen, how many electrons do I have to place in this? 5. So 1, 2, 3, 4. Where does the 5th one go? It has to go in a hybridized orbital. The hybridized orbital on the left or the right? On the right, because in the Lewis dot structure, that's where they are. And so now I can pair up these to form a sigma bond, and my hydrogen on the left in my structure here, I'm going to use to bond that. So I need to know what the hybridization is. I sketch out that orbital picture for each of the hybridized atoms, then put the electrons into it. And what I'm trying to do is mimic this Lewis dot structure. I'm trying to mimic that H single bonded to C, triple bonded to N, with the lone pair on the outside of N. And so then now I can overlap my p orbitals that are parallel to each other. So that's going to be this one, these two, top and bottom, because they're perpendicular. Well, they're in the plane of the screen. And then these ones right here are coming in and out of the board. And that would be my second pi bond. Is that helping? Yeah, so I can complete this. We can complete these if you would like. Well, I would like to. Let's do DSP3. So if you have a DSP3 atom, what's it gonna look like? So DSP3 means I have how many orbitals? 5. And there's no p's because all the p's got used up. So I'm just going to have 1, 2, 3, 4, 5. And the difference between DSP3 and SP2 is that in SP2, 3 are hybrid orbitals and 1 is a p. In DSP3, they're all hybrid orbitals because there's no p's. There's no p orbitals. And then what would D2sp3 look like? I'm going to have 6 lobes of electron density around it, and in this case all of those lobes are going to be shaded because there's 6 hybrid orbitals. Again, no unhybridized P's. So these are the pictures that you need to draw out. But then depending on the atom, you're going to have a different set of electrons in those orbitals. But the rule is that the lone pairs can only go into the hybrid orbitals. And quite honestly, if you draw out a Lewis dot structure, the lone pairs are kind of go into the orbital because you're kind of sketching the orbital picture to look like this. And I don't know if people saw, I went through, I don't think, what's today, Friday? I think it was Wednesday night, I recorded a little video on how to see the narrated answer keys. And it was in between Monday and Wednesday's modules, so that it shows you how to watch. There's a whole bunch of these problems in the folder, I think Monday's folder. And then there is a narrated answer key where I do exactly what I just did with me talking in the whole 9 yards. But you have to have your Adobe Acrobat at the latest version, and you have to download the Flash, the Adobe Flash, and make sure it's up to date. And then you'll see the PDF file come up. It's basically an animated PDF file, which is, I've never quite understood how they did that, but it's kind of a non-standard thing now. It's like Flash anyway, but that will work, I believe, on a Mac. And so you'll see it, and then you can move, then you'll see me draw and talk, and then if you grab the button or whatever, you can go to any problem you want, and then start playing from there. And you can download that to your computer so you can have it. So if you're having troubles with that, come and see me, or don't go to the help desk because they're a little busy today trying to get the internet back up and running. So, but that way, any of these problems, there are narrated answer keys. The other method of throwing it into the LiveScribe player, I think, are for later files, because they went to that, then they went away from it, and so. But that's available. So there's a lot of these problems on there that you can try, and then you can go back and see how I did it. Does that make sense? Help? Okay. I didn't bring any graded homework problems today, so I will bring those on Monday. Okay. But I'll probably ask you to do a couple there. So if you're having difficulties with that, you can always ask. Kind of make a little more sense? Like I said, you need practice. Those are in the Mondays folder. There's lots of practice problems there, and lots of me talking about them. What other things? Resonance, arrows. So the arrows meaning the arrows of the dipole-dipole moments,
Yeah.
not the arrows of resonance.
No.
Okay. So is something polar or not?
Yeah.
Okay. CH2Cl2. Is it polar or nonpolar? And then go with that, what's the strongest intermolecular force that two CH2CH-Cl2 molecules would undergo? So what do I have to do here? give me help. I'm lost. I'm not really, but give me some help. Anyway.
I mean, I would start with drawing the structure.
Okay. So I know carbon has to, hydrogens and chlorines have to come at the end of molecules. Hydrogens and halogens are always at the end. If you're trying to attach a C to a Cl to an H, nope, not happening. So hydrogens and halogens have to come at the end. So there's my structure. So now I need to basically make a correct Lewis dot structure. Okay, 1, 2, 3, 4. There's my Lewis dot structure. Okay. Polar or nonpolar? Polar or nonpolar? We sure about that? Really confident? Okay. Nobody's unconfident? Nobody's like, is that really polar? Hold on. Let me play the whole scenario out. Because for this one, okay, I can see that, and there's your dipole moment, right? So we bought the individual bond dipoles. Chlorine's more electronegative than carbon. Carbon's more electronegative than hydrogen. So all the bonds are adding up, which means that there is a non-zero dipole moment, molecular dipole moment. But for this one, if I do this and I do this and I do, whoops, the other way around, if I go this way and then I go that way, don't those cancel each other out? Good. Yeah, you don't. I can't do this. I can't do that analysis with just the Lewis dot structure. I have to put it into the Vesper geometry. So I have to put that carbon into a Vesper geometry. We haven't talked about tetrahedral. Let me show you. How do you represent a tetrahedron in two-dimensional space? So far I've done it like this. And then you have to kind of imagine that one of those bonds is towards you and one of them's away from you. So let's just use these wedge things and let's make it explicit. So when you have two bonds in the plane, regular bonds, they're in the plane of the paper, the board, the screen, whatever. And the bold one is coming towards you, and the dashed one is going to be behind. Okay? So that's how we can represent a tetrahedron in two-dimensional space. So let's see, how do I have it there? The regular bonds are like this. The bold bond is like that, and the dashed bond is like that. So here's your in front, behind, there. Okay. And this is where if you have kind of a set of those molecular models, it can sometimes make things a little bit easier to see. You can actually, if you search like methane or this molecule online, you might actually be able to see a model of it. If you don't have models and you want something, get 4 toothpicks and something gummy. A marshmallow would work. A gummy drop would work. Anything like that, and stick them in there at about 109.5 degree angles. If you need a tetrahedron, I think I have some upstairs. I don't think I got them all back last year, but I do have some. If you want to stop by, I'll have to dig out my. If I find these things like at half price books for $10, I usually just buy it. because I know I'm going to end up using them. So anyway, that's how we get the tetrahedron. So when I put my chlorine and my hydrogen into my tetrahedron, I've got chlorine and a chlorine and a hydrogen, and which one is that? Is that this one or is it this one? I don't care. They're all the same, right? Because I can rotate that molecule around. So then that would be my molecule. So our general rule is this. If you have a tetrahedron of any kind, it will be non-polar if all 4 positions have the same atom, exactly the same atom, right? So that would be if all 4 of these were hydrogen or all 4 of them were chlorine, it would be nonpolar. The fact that all 4 positions are not the same means it's polar, because the only way they can cancel each other out is if they're all the same.
Does it matter where you put, like, if you put the chlorines on the wedge of the dash instead of the
Yep.
hydrogen?
I can put them anywhere. It's the equivalent of me taking the molecule and just rotating it around. I'll show you that. Here. And I think I did this on one of the answer things on Piazza, but since I have my, whatever this thing is called, the ladybug, and it hasn't fallen off my cart yet, going through over the tiles and okay. So let's see, we are discombobulated here. So this would be the equivalent of using the Elmo over there, but I think with the internet out, the Elmo has some issues. Okay. So let me draw this out. So carbon, and then I want 2 chlorines, chlorine, chlorine, hydrogen, hydrogen. Okay. Then I want my 3-dimensional picture. So there's my 3-dimensional picture. So in this case, as I rotate it, it doesn't matter what my orientation is. So I can have any of those orientations of chlorines in front, behind, up, behind, any of those combinations just simply by taking this and by rotating it, like so. Okay. Now let's see. Let's see if the internet works. Because what I could do is I could try and download this and then show you how the pictures work. How it works. And yet this isn't attached. So what am I looking at here? I'm looking, number one, at what's called a space filling model, what the shape would actually look like, except there's no color coding in real life. So it all would just be kind of gray. But the color coding is the blue is the positive and the yellow is negative. So notice in this molecule then, I've got the negatives around where the chlorines are, and I've got the positive where the hydrogens are. To be a polar molecule, you have to have unequal charge on your surface. So in this case, we have delta plus in blue, delta minus in yellow. So imagine 2 of these molecules together. The yellow is going to be attracted to the blue, and that's going to make your polar or your dipole-dipole interaction. Okay. And the weird thing about this is, if I change this molecule, so I go back here and I make all 4 chlorines, you could say, well, so my chlorine, so having 4 chlorines, is this carbon tetrachloride a polar molecule? No. because now I have the same atom at each of the tetrahedral positions. They all cancel each other out. What does that mean for carbon tetrachloride? Because I have carbon-chlorine bonds, and they are polar covalent. So then I go to what the picture would look like, and notice what the picture looks like. It's all the same shade of green. It's all the same shade of green. There's no blue delta positive. It's all delta minus. So what it means to be a polar molecule is that you have a delta positive in your surface and a delta negative in your surface. Carbon tetrachloride is not polar because there's no delta plus on its surface. And so it is a non-polar substance. And it may have been one that you had in lab. If you did, it had a high boiling point, not because it had strong intermolecular forces, but because it's heavy, right? Because 4 chlorines and a carbon has a pretty high molecular weight. Did I talk about this as a dry cleaning fluid in this class? I can't remember which class I talk about what in. So this is a non-polar substance, and so this is why you would use it in dry cleaning to remove the dirt, because like dissolves like. Right? So that's what it means to be a polar versus a non-polar molecule. So the biggest ones I think that are a problem are tetrahedron. The other issue with the tetrahedron is if you put a lone pair in a tetrahedron, by definition, you've broken up the symmetry. So one lone pair in a tetrahedron is going to cause you to not have a cancellation. Right? And I did put this video on Piazza. So I had a nitrogen there, I think, for ammonia. And with that lone pair, it busts up the symmetry. So it would not be a polar molecule. Okay. Just for information, this morning we did some resonance structures in the morning class. So if you can get to that through YouTube, and just search YouTube and today's date and my name, and you would find like what I did. If you're interested, if they're interested in this, they could, I mean, I don't want you to watch 2 lecture videos a day, but if you're just curious, like, about that, email me, or again, post on Piazza, and I'll put up a video answer if I can't type it out. Okay, so Monday we'll be naming, so go through that. If you feel completely lost and your head's about to explode, stop before it fully explodes, and then we can go over it on Monday again with the parts that are really difficult. And I expect there to be lots of questions, but that's okay. That's the way we work through it. Okay, I'll bring the problems, the graded problems on Monday, and they'll probably be due like next Friday.